Okay, so here's a continuation of chapter 2. So for section 2, we're going to cover histograms. And a key concept here from section 2 is that while a frequency distribution is a useful tool for summarizing data and investigating the distribution of data, an even better tool is a histogram, which is a graph that is easier to interpret than a table of numbers. So on the left, we have a frequency distribution table like you saw in 2.1. On the right, we're going to cover histograms in 2.2. And this here is a preview of what histograms look like. Okay, so to define a histogram, it's a graph consisting of bars of equal width drawn adjacent to each other unless there are gaps in the data. So these are all equal width. If there are gaps in the data, like there are in this histogram, that means that there are no data points for that category. Okay, so for histograms, you'll always see these bars side by side and only gaps if there are truly gaps in the data. The horizontal scale here, it represents the classes or categories of quantitative data values. And then on the vertical scale here is our frequencies. So it's really similar to our frequency distribution tables, but now we see the data represented like this. And then just as we would tally all of those data points and put them into categories, these heights here correspond to the frequency values. Okay, so now some important uses of histograms, and there are a lot of important uses of histograms. So visually displays the shape of a distribution of the data. So visually displays the shape of the distribution of the data. And we can think of distributions in statistics as showing the possible values for a study and how often they occur. Next, histograms are useful because they show the location of the center of the data. Additionally, histograms can show the spread of the data, and we think of spread as the dispersion of the data or the extent to which a distribution is stretched or squeezed. So in the red here, this would be an example of squeezed, and in blue would be an example of stretched. Next, histograms are really great for identifying outliers, where an outlier is a data point that differs significantly from other observations. So on this histogram here, if we see this data point that's further away from the other data points, we might have an outlier, but we would need to do some calculations to prove for sure whether it's an outlier or not. But a histogram helps us more easily visualize that. Okay, we also have relative frequency histograms. So it has the same shape and horizontal scale as a histogram, but the vertical scale here is marked with relative frequencies instead of the actual frequencies. So if you'll remember in 2.1, we had something similar for our frequency distribution tables. And if you need a refresher on how to calculate relative frequencies, go back and watch the lecture on that one slide. I went ahead and showed you this formula again to either calculate the relative frequency for a class as a frequency or also as a percentage. So this graph on page 62 happens to be the percentage representation of this relative frequency histogram for the McDonald's data. And to remind you how to calculate those percentages, you want to find the total number of frequency values that totals up to 50. Then you find the percentage of that specific category or class out of a total of 50. So to find that percentage, you would take 11 out of 50, multiply it to get into a percentage, multiply it by 100%. I also want to point out that on the x-axis, you can see that the divisions of the histogram bars are actually the class boundaries. And so we learned how to figure out what the class boundaries are in Chapter 2, Section 1. So just one other thing I wanted to point out. So the class boundaries are the numbers on the x-axis, and then the percentages are what is displayed on the y-axis of this data. Okay, and in statistics, of course, we're always critically thinking. So we're not just crunching numbers, looking at the data sort of blindly, setting up our graphs blindly. We need to be critically thinking about our data. So with histograms, you can remember this acronym of CV dot, where C is the center of the data, V is the variation, so think dispersion or spread, which we just talked about. D, the shape of the distribution. O, whether there are any outliers. And T, time, where time can tell us if there's any change in the characteristics of the data over a period of time. Okay, on this slide, we're looking at common distribution shapes. On the top left, we have a normal distribution. It looks like a bell-shaped curve. On the top right, we have a uniform distribution where the data are almost the same in each class. So that's why we call it a uniform distribution. Here on the lower left, we have a histogram that's skewed to the right or positively skewed. On the bottom right, we have a histogram that's skewed to the left or negatively skewed. And we'll go into more detail on these three. First, in normal distribution, this histogram is roughly bell-shaped, so that's how we can remember it as a normal distribution. Think that it's bell-shaped. We also touched more on normal distributions in Chapter 2, Section 1. So remember, we wanted to see some symmetry in the data. We wanted to see frequencies start low, become higher. We have one or two of the most abundant frequencies, and then it dips back off to lower frequencies. Next, we consider something skewed or skewness. If a distribution of data is skewed, it is not symmetric and it extends more to one side or the other. Okay, so that's different than a normal distribution where we see this symmetry here and the data does not extend more to one side or the other. So the first example of a histogram that's skewed is when we have data skewed to the right or positively skewed. We can identify that this is positively skewed because we have a histogram with a longer right tail here. So a histogram that has a longer right tail here, that's positively skewed. That's also known as skewed to the right. Okay, and for the opposite, we can have data that's skewed to the left or negatively skewed. And so you'll see this has a longer tail of data on the left. So a longer tail on the left, the data is skewed to the left and therefore is negatively skewed. So now we're going to talk about assessing normality with normal quantile plots. We're going to go through some criteria for assessing normality with normal quantile plots. So we're looking for a normal distribution where the pattern of the points in the normal quantile plot is reasonably close to a straight line. And another criteria here, the points do not show some systematic pattern that is not a straight line pattern. Now for normal quantile plots that don't have a normal distribution. The population distribution is not normal if the normal quantile plot has either or both of these two conditions. The first being that the points do not lie reasonably close to a straight line pattern, then we would not have a normal distribution. Also, if the points show some systematic pattern that is not a straight line pattern, then we also do not have a normal distribution. And we'll go into some examples. Now recall, for a normal distribution, the points do not show systematic pattern that is not a straight line pattern. And also the points are reasonably close to a straight line. So this is an example of a normal distribution. So the points are reasonably close to a straight line pattern, and there is no other systematic pattern that is not a straight line. We know there's no other pattern other than a straight line because, for example, here we have 2 data points. There's a gap here. We have 4 more data points. We have 1 data point here, and then we have 3 here. So there's not really a pattern in these data points other than them falling essentially on a straight line. Now, again, recall for a plot that does not have a normal distribution. So the population is not normal if the normal quantile plot has either or both of these following conditions. If the points do not lie reasonably close to a straight line pattern. Okay, so something like this is an example of not a normal distribution. Those points do not lie reasonably close to a straight line. The other condition here for not a normal distribution is that the point shows some systematic pattern that is not a straight line pattern. So although in this example, the points do fall essentially on the straight line, it's not considered a normal distribution because there's another pattern going on with the data points. So again, although these data points do fall on that straight line, there's also this other pattern going on where these points seem to appear on the x-axis about every 0.95 units. So you have a data point here, 0.95, we have another data point, 0.95 away, we have another data point, so on and so forth. So because there is that additional pattern, this is not considered a normal distribution. Okay, so now after watching 2.2, you should be able to complete the second half of that example on page 1 of your student outline. And now you should have the entire packet filled out. Okay, next will be chapter 2, section 3. So make sure you're keeping up with the material, you're keeping up with the homework, you're reaching out to me with any questions that you have. Talk to you all very soon.